this is just for your own revision and stuff. Okay, so we started out, and the first thing we looked at was coordinate geometry. And Pythagoras. And showing how we can use that to calculate the length of a line or a ray. So that particular set of formulas. Then we looked at trigonometry. So sine, cosine, tangent, inverse sine, inverse cosine, inverse tangent. Everyone get that? And the next thing that we looked at was the unit circle. And the polar to Cartesian and Cartesian to polar coordinates. Being able to calculate angles from a vector and vector from an angle as well. Alright, so it's very important to know how to do that. And be able to draw that unit circle and be able to derive a look vector from an angle in 2D. Okay, so that was the next thing we looked at. Then we looked at vectors. So then we talked about addition, subtraction, multiply by a scalar, and then multiply by two vectors. And we discovered that there was two ways to multiply vectors. There was what we called the dot product, and then there was another type of multiplication called the cross product. The dot product, which gives us a scalar, and the cross product, which gives us a vector, which is mutually perpendicular to the two vectors that you multiply together in the cross product. And the dot product, we realized that you can use the dot product in this equation, which is theta equals the inverse cosine of A dotted with B over the length of A times the length of B. And in addition to knowing what each of these things does and how to solve problems using these mathematical tools, you also need to know how to code them in C++ using the GLM maths library. So how to code these solutions in GLM. Alrighty, so then we did vectors. Next thing we looked at was matrices. And we looked at how to multiply two 4x4 matrices and how to multiply a 4x4 by a 4x1 matrix, giving us a 4x1 matrix at the other side. And then we realized that we can use these matrices to do transformations. And the three transformations are the translation, S, scaling, and rotation around an axis. So, that was what we did with matrices. Once we had done matrices, we looked at the relationship between matrices and the rendering pipeline. So the relationship between rendering pipeline is the stuff like the world transform, to the view transform, to the projection transform. Alright, and how you set up each of those matrices. So we learned that every model in our scene has got its own world transform, which is made up of its position vector, its scaling vector, and its quaternion for rotations. And the view transform is made by using the GLM. What's the API we use to make the lookat? I told you, it's the lookat. So you use the lookat call to make the view transform. The projection, you use the GLM colon perspective API call, and understand what the parameters to that API are. What you need to pass into that, for example, the aspect ratio, what else do you pass in? The near clip plane and the far clip plane, things like that. So then we did all that stuff to do with OpenGL rendering. And we briefly mentioned shaders, which we'll talk about a little bit later in the course. So then, you kind of probably briefly touched on this, but I remember everyone being kind of tired when we were having the discussion and not really getting it, but was the idea of the scene graph. Can anyone remind me what a scene graph is? Anyone remember? What is a scene graph?
Not the 2D representation of 3D scene.
No. No. What's a scene graph? Do you guys, yeah, when you get a chance, you should definitely look at the notes that I do for every week as well. You know, don't just rely on the lecture and your own notes. But I have a whole set of lecture notes that I'm working on week by week, and there's a load of lecture notes about scene graphs in my PowerPoint slides. I don't remember what they are. Scene graph is just a list of everything that you're keeping track of in the game engine. The nice and interesting thing about a scene graph is that you can create relationships between different things in the scene graph. So for example, you can have a parent-child relationship in a scene graph, and the child's world transform is created from its own position, quaternion, and scale, but then you multiply in the parent's world transform as well, and then the child becomes attached to the parent. So when the parent rotates, the child also rotates. That's the concept of a scene graph. Have a look at the notes again, right? just for some revision on that topic. We also talked about, and you have a full question on your exam, by the way, on scene graphs and component-based game engines. So the idea of components, you can attach components to other components in a game engine. The way I've implemented in BGE is that everything is a component. But I think the standard way to do it, because I was having a good talk, I gave a talk in a thing called Fermented Poly about this on Tuesday, and the standard way is that you have a game object with a transform, and you can attach things to the game object which don't necessarily have a transform, but they affect the object's transform. That's the way it's normally done. We'll do a revision class on that at some stage, right? But that's very important. So a full question on your exam about scene graphs and components in games. And it's related, to this idea of parent-child relationship in games, right? So that was that. Then the next thing that we did was quaternions. And maybe we'll spend a little bit of time just revising all the important things to do with quaternions. So number one thing that we know about quaternions. How many dimensions does a quaternion have? It's a 4D thing. Okay, so it has an X, Y, Z and a W component. So we know that a quaternion is a 4D thing. What else do we know about quaternions? How do we make one? What do we need to make a quaternion? How many people learned the poem like I told you to do that? Jesus. Okay. It's a 4D thing. Next thing we know about quaternions, to make a quaternion you need a axis and an angle. An axis of rotation and the angle of rotation. And I showed you how you can make one yourself if you really need to from the axis and angle, but you don't need to ever make one like that. You use the API axis angle. You pass in the angle axis, and you pass in the angle of rotation as in degrees, and you pass in the axis of rotation as a vector, and that way you can make a quaternion from something. So we have axis and angle is how we make one. When we make quaternions, certain quaternions represent rotations, and certain quaternions don't represent rotations. Ones that don't represent rotations, what do we call those? We call those pure quaternions. And a quaternion that represents a rotation must be normal. So it has to be normalized, right? The X, Y, and Z and the W component, you square the root of all that sort of the same way as you normalize a vector. It must be normal, otherwise it doesn't represent a rotation. And if you guys were playing with the lab and you didn't necessarily normalize the axis of rotation, you would make a quaternion, and then you go and make a matrix out of the quaternion, and you discover that it actually scales the model. Because it has to be a normal quaternion, otherwise it doesn't do the job. It won't actually rotate it. So we make one from that. It must be normalized. And then we discovered that we can rotate vectors by quaternions. So what's the equation for rotating vectors by quaternions? It's W equals, and you need to know this off by heart. You should just rattle it off, right? At some point you need to learn that poem off by heart, right? Not just for your exam, but also for interviews. And it's just for general, knowledge of how game engines work. It's really important. So can you remember, it's W equals Q times W times the inverse of Q. And that's how you rotate a vector. And we make W from what? How do we get W? Yeah, it's the pure quaternion made from the vector. So we take the X, Y, and Z of the vector, and you set the W component to be 0. And then this is how we invert a quaternion. To invert a normal quaternion, you just negate the X, Y, and Z components of it. And if you take this and you multiply this out together, you will discover that you will have effectively rotated the vector by a quaternion. I remember we wrote a very small program at the end of last week where we generated a quaternion, we generated a vector, multiply them out using this equation, and you notice that this has the effect of rotating the vector. So quaternions are the standard way to store in Unity, for example. When you get a Unity transform object, you can create a quaternion. That's how you do rotations in Unity. That's how every game engine in the world does rotations, using this formula, right? And eventually, of course, the quaternion by itself is of limited use, because in order to actually do the transformation, we need to make a matrix out of it. So at some stage, you need to take the quaternion and make a matrix. Sorry, one thing I forgot to talk about actually was, while we were up here talking about OpenGL and all of this stuff, we also talked about how to make an FPS camera by implementing walk, strafe, the operations then for rotations, we call them yaw, pitch, and roll. So implementing yaw, pitch, and roll as well, using vectors. So today I'll show you how to use, I forgot to start that bloody thing again, did I? Oh no, the light's on, it's recording. Yeah, so today we'll look at how to do rotations using quaternions, and we'll make what's called a Quaternion camera, which is a better way to do the camera. Alrighty, so that's, I think, everything that we did so far on the course. Have I left anything out?
Gimbal lock?
Gimbal lock, yeah, sure. Maybe I'll just throw that in there, gimbal lock. And looking at alternative ways of representing rotations in the game engine, such as what we call Euler angle sequences, and comparing maybe a quaternion with a look vector to see that they actually represent slightly different things. The look vector, of course, represents the direction something is looking. So this has a look vector and it has a quaternion. Its quaternion will tell you whether it's going this way or this way, which is something that the look vector won't tell you. The look vector just tells you in which direction it's going. So you could be moving in this direction, and your look vector is the same as if you're moving in this direction here. Everybody follow that? But your quaternion will tell you whether it's upside down or what direction it is. Okay, so that's all the stuff we did to do with, that's everything so far. There's a whole pile of maths there, a whole pile of really interesting and cool magic, which you can do lots of really cool and amazing things with. For example, the example that I gave last week was combining the orientation quaternion from the Oculus Rift with the orientation quaternion from a gamepad. There are other ways to do that, but I think the simplest and quickest way to do that is get the two quaternions and what do you do with them? How do you combine quaternion rotations? If I have a rotation that represents one rotation around a particular axis, and I have another rotation and I want to combine those two rotations together, in other words, do one after another, have a guess, go on. Try it. I'm not going to give out to anyone if they get it wrong. Go on, Brianna, you said it. Multiply the quaternions together. So multiplying two quaternions gives you a quaternion which is also normal. If the two quaternions are normal, multiplying them together, you get a quaternion which is also normal, and it has the effect of combining the two rotations together. So I have something, for example, that gives me the yaw, right, based on the Xbox controller, based on the thumbstick. Okay, so it's going to allow me to create a yaw quaternion from that. And I just take that and I multiply it with the quaternion I get from the Oculus Rift, and that has the effect of doing the yaw first and then doing the Oculus Rift rotation, which gives you the rotation, the full 3D rotation. You multiply two together. And then, of course, I wanted my thumbstick, I wanted my joystick on the game controller to actually control the direction in which I'm moving. So I have to recalculate the look vectors for that, so that when I say walk on the Xbox controller, it's using the combination of the two quaternions together to do the walk. So at some point, actually, you have to keep your vectors in sync with your quaternion. Your quaternion is going to give you the orientation. But if I'm orientated in this way and then I want to walk in this way, I need a look vector to do the walk. So you have to keep them in sync, right? So actually, let's take a look at how to do first-person camera using quaternions, right? So the difference between this and the camera model, can I grab a page just to wipe the board off somebody? No. The difference between this and the camera that we did before, the camera that we did before was a vector camera. So I keep three vectors, the look, the up, and the right. And for example, if I'm yawing, which two vectors do I rotate? I'm yawing, which of the two vectors am I rotating? And what am I rotating around? So I'm rotating around the Y, yeah? It's the X and Z, so it's the look vector and the right vector get rotated in the effect of the yaw. If I'm doing a pitch, which two get affected? So it's the one that you're looking, and it's the one that's the up and down one, right? So your up vector and your look vector get modified when you're doing a pitch. And when you're doing a roll, yeah, so the Z doesn't get changed. Essentially, it's not the Z, it's the local axis of it, right? If you were just looking down the negative Z axis, if you were in your basis space, then yeah. But of course, if you're doing a roll, then it's actually the up vector and the right vector that get modified when you're doing a roll. Because your forward vector doesn't change, or your look vector. It's called a forward vector in Unity. Is that okay with everybody? So it's very important how you know to program those in a vector camera model. The better way to do the camera is to basically decide that the orientation quaternion is the thing that controls everything. And then you just rotate your vectors to match the quaternion. So walk and walk and straights don't change. The things that change, let's imagine that yaw changes, right? So yaw, again, is going to take okay, so the concept here is, if you remember how yaw works, I'll just write yaw up for a vector-based yaw, right? For a vector-based yaw, what we want to do is take the look vector and rotate it a little bit around the global look vector. So how do you do that? If you remember, you make a rotation. How do you rotate anything? Huh? Yeah, so we can make a rotation matrix, and we can transform the vector by a rotation matrix. Alright, that's how we move or do anything with matrices. So I'm going to go something like GLM : rotate, and then you pass in the angle, and then it's going to be the basis up vector, and then I'll just go m equals that. So that's going to give me my rotation matrix. And then I want to transform my vectors by that rotation matrix. How does that work? How do you transform a vector by a matrix? First of all, what's the problem with the vector? Yeah, so we need to make a 4D vector out of a 3D vector. So you go something like GLM : vec4 temp, where the temp vector is going to be equals to GLM : vec4, and then you pass in the look vector, and you pass in 1. And that will take the look vector, and it will make the XYZ components equals to the XYZ components, and then it sets the last component to be equal to 1. So now I have a 4D vector. So now it's legitimate to maybe multiply this 4D vector by this matrix, because we've got 4 by 4 thing that we can do. So you can go something like temp equals temp. Can't you remember if it's temp multiplied by m or if it's m multiplied by temp? Can anyone remember? I can't remember. I'd have to look up my notes. But it's one or the other. The message is here that I'm basically multiplying this matrix by this vector, and then this is going to give me a rotated version of that vector. And then once I have a rotated version of it, I can go look dot x equals. In fact, I think you can just do look equals GLM : vec3 temp. And I think the constructor for the vec3 just ignores the 4th parameter. And so what I'm doing here is basically taking a 4D vector and changing it back into a 3D vector. So I do that with the look, and I do that with the right, and then I've implemented a yaw. And I've rotated the look vector and the right vector by using a matrix. Everybody follow this? I'm not 100% sure if the code is exactly as you would type it. I can't remember whether these go this way or this way. And then I'm pretty sure you can construct a vec3 from a vec4 that way. But you understand the principle? Everybody happy with the principle of that? So the alternative way to do this is, instead of doing this and basically rotating the matrices, what we do is we rotate the quaternion, and then we use the quaternion to update the look vectors, right? And it's the same call. You don't even worry about the look vectors. And this is a better way to do rotations. So if I want to do a yaw, using the Quaternion Camera model, which is, like I say, a much better way to do it. So think about it. We have this quaternion which is representing the object's rotation, and I now want to get that to rotate a little bit more. So first of all, I have to, to combine one rotation with another rotation, what do? We multiply 2 quaternions together. So what I need to do is generate a quaternion which represents this angle around the basis up vector, and then I just multiply it into the quaternion, and I get the new quaternion for the object's look vector. Sorry, for the object's orientation. Yeah. So, first of all, you just go, your quat Q is going to be equals to GLM : axis angle. Sorry, it's angle axis, isn't it? And we pass in the angle, and we pass in the basis up. So that's going to give me a quaternion to represent by how many radians, by how many degrees I want to yaw. Because don't forget, this axis angle takes this in degrees. So now I have a little rotation quaternion. This is going to give me a rotation around the basis up vector by theta radians. I should really call that theta. So to calculate the new quaternion is really simple. I have a quaternion called orientation. Orientation is just going to be equals to the new rotation well, let me call that rho then. Multiply by orientation. And that's how you do yaw using quaternions. Simple as that. So what's happening here, right? What's happening here is I have an orientation quaternion, which is, it's going to start out being the basis quaternion. The basis quaternion, not the basis quaternion, the identity quaternion. The identity quaternion represents no rotation. Alright, there's a quaternion, the same as the identity matrix, there's an identity quaternion which represents no rotation. And that's the way the object's initially orientated. And you have to decide what's that relative to. So but in general, it's going to be relative to looking down the negative z-axis. In other words, I load up my model in local space, what way is it facing? No rotation has been applied at that point. So then I rotate a little bit around the up vector, the basis up vector, and I just multiply that into the object's quaternion. And then that way I'm just combining this little bit of rotation with the existing rotation. Does everybody understand that? Everybody understand? That's so, like it's magic, right? I don't know how quaternions work or why they work, but they work. So you just have to assume that the quaternion represents some sort of rotation or orientation, and you're just adding in a little bit of yaw rotation. And this is how you generate the yaw rotation by basically saying theta radians around or theta degrees around the up vector. And that's going to give you a little rotation that way. So then I just multiply that way into my current rotation. Is that okay with everybody? So there's a couple of little issues then. So that's how yaw works, right? Yaw is pretty straightforward, right? I want you guys to try and write pitch. But keep in mind, pitch is, there's one little caveat with pitch, isn't there? Pitch is looking up and looking down. It's very disorientating if you look all the way up and then you start going backwards. It's very disorientating in a computer game. So you want to avoid it. What you want to do is make sure that you can only rotate up as far as here and then you can't go any further, or you can only rotate as far as here and you can't go any further. Do you understand? And then the pitch we decided was a rotation around which axis? It's whatever the angle is, whatever its vector is, it's the right vector. Now if I'm looking in this direction, I want to pitch up and down like this. That's called the right vector, and that's how we do that. You guys try and write the pitch with it, and then we'll take a look at the solution. And maybe I'll throw it up on the PowerPoint slides, right? I actually have slides for this now. I updated the slides on quaternions during the week, so the ones that are up on web courses are slightly more up to date than. In fact, I had none of last week, but there's a very good set of lecture notes on this, which I might find useful to read. And I'm always kind of a week behind the lecture notes. But yeah, when you're thinking about this, think about how you might limit the rotation so that you can only go maybe up so far, not quite straight up, right? And then not quite straight down. I'll pause the camera for a minute while we have a think. Okay, so we'll just do this anyway because I want to move on to this physics programming so you can do a little physics lab next week, right? Looking at this here, you can see that the pitch, very straightforward pitch is just going to be taking this rotation, and instead of making this around the bases up, you just make it around the right vector. So that's going to give you a rotation of theta degrees around the right vector, and you multiply it into the orientation, and that's the simple version of pitch. But the issue here is we only want to do this if we're not pointing more or less straight down or straight up, right? So how that needs to work is like this. Ideally, we want to do it without calculating the actual angle. So let me just think. I think this works a bit easier if you try and visualize it from a side-on view, right? Say that's the axis of rotation there. That's your straight up vector, and that's your straight down vector, and that's your character. And let's assume that that's your look vector there, right? So your character, we'll say, currently is looking more or less at the limit, and it's almost at the limit of where it can go straight up, right? If I was to look straight up, okay, this is the look vector, and this is the basis look vector, and this is the basis down vector, I'll just call it that, but it's basically just, this is 0, 1, 0, this is going to be 0, minus 1, 0, and then you take your look vector. If your look vector and the basis vector were basically straight up, what would the inverse cosine of that be? Or what would the cosine, what would the cosine of that be? It will be 1. Alright, because we're looking at a cosine of 0 radians. So you decide what the threshold is. And an interesting threshold I find which works quite well is 0.95. Alright, just because it's nearly 1, and you allow yourself half of a whatever. I don't know what the unit is in that case. It's not degrees or radians because it's the inverse of that, right? So we can get the dot product between this and the dot product between this. And if I discover that the dot product between these two vectors is less than 95, or sorry, less than 0.95, sorry, greater than 0.95, it's almost approaching. I don't want to do the operation. I don't want to allow them to push even further up. Do you follow? But then you have to figure out, okay, I don't want them to allow them to go this way, but I do want them to allow them to go this way. So you have to figure out, you know, it's a compound if statement. You have to check to see which direction you're going to rotate. Now we know with OpenGL, our rotations are clockwise or counterclockwise. They're counterclockwise, all right? So that means a positive rotation is going to be in this direction here. And a negative, so that's a positive rotation is going to bring me in this direction. And a negative rotation is going to bring me in this direction. So I think the if statement needs to check two things. First of all, checks to see if you are going in a positive direction and your rotation is greater than 0.95, then you don't do the rotation. Alternatively, I mean, you can take this vector as well, and interestingly, if you go all the way down here, you'll get minus 0.95 as your inverse cosine. Alright? Or you could do 0.95 and you could use the down vector, and you just check the opposite thing. So on your compound if statement basically just checks to see if your rotation is 0.95 or greater and you're going on a positive rotation, you don't allow the rotation. Alternatively, if you're minus 0.95 and your rotation is negative, you don't allow the rotation. And that's the way you limit the person from going beyond the bounds. And you see that the cool thing about this is that you don't have to calculate any inverse cosine. You just multiply those two vectors together, check to see, make sure they're normal, of course, which they are normal anyway. And then, you know, you check those values. Cool. And there you go, limit it. I'll show you what it looks like in C++ code, right? So here we go. This is what it looks like in C++ code. So first of all, I do this inverse cosine of theta. So this is the, you know, the dot product of the two vectors. So I just get the look and the basis up. So the basis up is 0, 1, 0. This is my current look vector. And then my threshold is 0.595 radians. So I check to see, I'm passing in an angle here, which direction I want to go. If angle is less than 0, then that means I'm going which direction, clockwise or counterclockwise? That's clockwise, right? So if I'm going clockwise rotation, and my inverse cosine of theta is less than minus the threshold, so in other words, clockwise, if I am going in this direction, and I am less than 0.95, then I don't allow the rotation. Or, if the angle is greater than 0, in which case I'm going a counterclockwise rotation, and my value is actually greater than my 0.95, then I just return. I don't permit the rotation. So I'm allowed to go down if I'm almost at the top, and I'm allowed to go up if I'm almost at the bottom. And that seems to work pretty well for limiting the rotation. You like it? I think it's pretty cool, right? You know, so again, this is an example of maybe using some cool maths that we've learned on the course to do something, you know, kind of brilliant. Here's a little magic spell. That's how you do those things. That's how games work. Alrighty? So, one last thing that we have to consider. So now I'm using the Quaternion as the master thing to control the orientation of the object instead of the vectors. So I update my Quaternion each frame based on, you know, the mouse look. But if I want to keep walking in this direction, depending on my Quaternion, or I want to go strafing to the right, then I also need to update my vectors based on the Quaternion. And that's the second thing that you need to do. So that actually is surprisingly easy, and you guys already know how to do it. In order to keep everything in sync, all you have to do is you just rotate your look vector. Oh, sorry, you don't need to do that. You guys tell me, how do you calculate the new vectors? I have a Quaternion which is giving me my new orientation, okay? the magic box, the thing, the quaternion is telling me what way I'm orientated. The basis quaternion is going, or the identity quaternion is going to be no rotation. My vectors are the look vector, the up vector, and the right vector, the basis ones, right? If I don't apply, just when the model is loaded, my quaternion is equal to the identity quaternion, in other words, no rotation. After a few frames, the user's yawed around, pitched it a little bit, I now have a new quaternion which represents the object's orientation. How do I calculate the new vectors? Because I still, you know what I mean? Look at this, right? If you look at this program here, look at yaw. There's yaw, look, it's just 2 lines. Okay? But, of course I need to do something else, because watch this, right? When I yaw again being rotation around the up vector, or the basis up vector, look at me yawing. I've yawed all the way over here, but when I press W, I'm doing, I'm basically moving in the direction of my look vector based on my position equals position plus look multiplied by time delta multiplied by speed. That doesn't change. Again, I'm yawing over here, and I'm still able to move in that direction. So you see, I need to take the quaternion and make new vectors out of it so that I can still walk in strafe. How would we do it? It's actually really simple. If you can get your head around what the quaternion does, you actually already know. And if I show you to, you'll go, oh yeah, that's obvious, of course. Look, I can still strafe. Regardless of what my quaternion is, the strafing still works. Because I have a right vector and I have a look vector. Any ideas? Cross product of what? And what we try to get. Don't forget, what I'm trying to do is get my look vector, because I need to move in a particular direction. And I need my right vector, because I want to strafe in a particular direction. I have this magic thing called the quaternion, which tells me which way I'm orientated. And when I yaw and pitch, that's what gets updated. If I didn't do this last bit, watch what will happen. I'm going to put this thing out for a second, because I don't want to rob some of you of the joy of realizing this for yourselves. Oh, perfect. There it is. Right, so I'm going to comment out this code. And watch what happens now. Okay. So, here we go. I am walking, no problem. I am strafing left and right. Cool. I'm now going to yaw. Oh, where's my yaw gone? Okay, this actually is even broken the yaw. Why is that broken the yaw? Yaw and pitch no longer works. Okay. Why does it need to do that? The yaw should still work, because it's rotating around the basis, so it doesn't do this. Oh, okay. For some reason it's broke. I'm not quite sure. I would have thought you can still rotate, so apparently not. Okay. Anyway, you can see that you need to keep your vectors in sync with the quaternion. How do we do it? I have a quaternion which represents the orientation. You need to calculate new look vector, new right vector, new up vector. When you see it, you'll kick yourselves. It's kind of obvious. What's a quaternion do? It rotates. What can you do with a quaternion? You can rotate rotate anything. You can rotate a vector with a quaternion, right? So what vector do we need to rotate to calculate the new look vector? The basis look, Alright, so you take your 0, 0, minus 1, you rotate it by the quaternion, that gives you your new look vector. Do you understand? And do you understand why it does? Because the basis quaternion, the basis vector, 0, 0, minus 1, is what way your object is pointing with no rotation applied to it. You then rotate your object. You also want to rotate the look vector. So the object is being rotated because the quaternion is being used to make the world transform matrix. So that's why the object appears to get drawn rotated. When you want to move in that direction, you need to calculate, well, what's the new look vector? Okay, I'm looking this way straight away. My object is rotated. I just need to rotate my look vector as well. So you just rotate the vector by the quaternion using this, q times w times the inverse of q. And here's how the code works, right? How many people figure that out? It's obvious when you think about it, isn't it? Isn't it obvious? Everybody say yes. Yeah, good, good. It's obvious. You need to keep everything in sync, right? So every time I do my yaw and pinch and stuff, every frame in fact, I also have to calculate this. Recalculate the vectors. The look vector is the basis look multiplied by the quaternion. The right vector is the basis right multiplied by the quaternion. And the up vector is the basis up multiplied by the quaternion. You know, my quaternion is representing some new orientation. Calculating the vectors, you know, that's how it's done. Okay, so, and how does rotate vector work? Well, we kind of wrote one in the class last week. It's just that q times w times inverse of q thing. It's nothing complicated or fancy. I'll just right click on this, choose coach definition. And there you go. You know, we wrote one of these, didn't we? Just rotating the vector. So first of all, I calculate the inverse, and we said to this, all this is going to do here is just going to get the negation of the x, y, and z components of q. It's just a formula. You just plug the numbers in and it works, right? And then the w component is equals to the w is 0, the x, y, and z are the x, y, and z of the vector. So that's me making a pure quaternion from the vector. You know, there's a line in the code. Rotate vector by quaternion, you multiply vector, quaternion, inverse quaternion, quaternion vector, inverse quaternion, and you rotate stuff, you see. Here we go. So that's the w bit, and then you go w equals q times w times the inverse of q, and then you make a vectory out of the x, y, and z of the w. That's a really, really cool magic spell. It's a brilliant thing to be able to do. You know, you'll find infinite ways of making use of that. To rotate things by a quaternion, you just plug them into this little equation, and you can write this in C# and Java, whatever, and it just works. And that's how it's done. So now we have a Quaternion camera, all right? Where the quaternion is the thing that determines the orientation, and we use vectors to implement walking and right. Full question on your turn as well. Okay. Will we take a 5-minute break? Okay. I'm going to do some physics programming. Oh, you want? I'll show you the solution to the lab as well. Actually, maybe I'll just show you the solution to the lab, and then we'll take a break, because then we can sort of draw a line under quaternions for a little bit. Okay, so if you remember, this was the lab. The spaceship on the right, which is controllable using the keys, and can rotate and also go up and down. Oops. I'm going to use the arrow keys. Which are the keys? O and L. Okay. How do I rotate it? O and L. Huh?
Arrow keys.
Oh, is it the arrow keys? Okay, there we go. There's the arrow keys. And there it is rotating. And then I press the space key and it slurps, right? So remembering that a quaternion slurp gives you a quaternion which is T between the first quaternion and the second quaternion. It's another really, really cool magic spell. This is how all sort of animation is done in every game as well. You know, you store a quaternion here which represents the orientation of this thing, and then you have the next frame, or the next key frame, and you say, right, I want it to rotate here. And then it will slurp the rotation between, you know, if you want to get the intermediate frames, that's how animation works, right? So, in this example, we have 2 little problems to solve, and this was lab 7. So here's the solution to the first part, right? I'll just show you this because it's I actually commented it out. But basically, to make a quaternion would require an axis of rotation and an angle of rotation. So the axis of rotation, first of all, I calculate the two ship 2 vector. So ship 2 position minus ship 1 position. A vector that will bring me from ship 1 to ship 2. Then I normalize that vector. So my axis of rotation then is the cross product between the basis look and the two ship 2 vector. So when I'm even saying this, right, you need to visualize this in your head, right? I'm calculating a quaternion which is going to rotate me from the local way that this object is rotated so that it faces the other thing. And in its local space, it's pointing down the negative z axis. I have something over here. I need my axis of rotation straight up like that, and my angle of rotation is going to rotate me around here. So you calculate the axis of rotation by getting the cross product. You have to normalize it, and if you don't normalize it, it will screw up the quaternion generation. And then theta is equal to the inverse cosine of the dot product of the two ship 2 vector and the basis look. So I'm making it from the angle of rotation to the axis of rotation. The really cool thing about this quaternion way of doing things as well is that you don't have to worry about interior and exterior angles, because the axis of rotation will flip if the things are the opposite way around. If you're looking this way and ship 2 is over there, and you get the cross product, it's going to be the up vector. On the other hand, if ship 2 moves all the way over to here, then what you get is the down vector. So it's actually the same angle of rotation around the opposite axis, which is essentially a rotation in the opposite direction. So you don't need to worry about interior and exterior angles for quaternions, because the axis takes care of it. You flip the axis when the things go either side. The cross product does that for you. Up vectors and that sort of thing. So that's the simple code, and then we make the quaternion from the angle at the axis. So the slurping thing is basically just a variation on that, right? What I want to do is, if I press the space code and I'm not already slurping, I set slurping to be true, and I set my from quaternion to be whatever way the ship is currently pointing. I want to rotate from my current orientation to the new orientation. And then this code here is the same. I just calculate the quaternion that would bring me to the new one. And that's my two quaternions. So this is the same code. I just get my from quaternions, my current orientation, my two quaternions, where I want to go. And then I just check to see if the slurping flag is true. And if the slurping flag is 2, I set my orientation being a mix of the from quaternion, the to quaternion, and the t value. And t, I have to remember up here to set t to 0. And then I just add a little bit to t each frame around as I'm slurping. And I'll get quaternions that will bring me gradually from the from quaternion to the to quaternion. And as soon as t becomes greater than 1, that means I'm done. So I set slurping to be false. Does that make sense? Is that logical? Cool. Alright, good thinking. Again, I think this is a pretty serious question on your exam. Something that I almost always ask my quaternion slurps. But, anyway, we'll have plenty of time for exam prep classes later on in the course, right? Right, so let's take a 10-minute break and we'll do a little bit of physics.